Okay, so now we're going to go through and talk through our circular motion here. So last week we introduced it. We went through a couple different examples of figuring out that acceleration is directed towards the center of the circle. So it's centripetal force. So the force and acceleration are inwards directly towards the center, and that the velocity is always going to be tangent to its circular path. So we need other things to know are the difference between rotations and revolutions. If it has an internal axis, like the Earth turns around its own axis, right, once every 24 hours, that's a rotation. A revolution is basically if the axis was outside of the body, and then you rotate around that. You complete a lap around that. So like the Earth completes a lap around the sun once every 365 and change days. Okay, so tangential speed, velocity, period, frequency, centripetal force, centripetal acceleration. So different little characteristics: angular speed, tangential speed or linear speed, frequency, period, different things to know. So the frequency is defined as the number of revolutions per period of time. Usually we're going to say, you could also say, let me add this here. I don't know if it's going to add it to yours or not, but hopefully it does. Thank you. Cycles per second. The number of cycles per second. So I don't know if it has made that on yours or if it will update, but if not, you guys can add that as well. It's updating. All right, perfect. So the unit that we're going to use most often is called hertz. It is basically the number of cycles completed per second. You can sometimes see things as RPMs, but we really don't want it in RPMs. We want it in revolutions per second or rotations per second, whatever it is per second. So if you have something in RPM, divided by 60 to put it into hertz, simplified or abbreviated capital H, lowercase z. Then you have the period. The period is the time it takes to just do one complete circle, one complete lap around a track, anything like that, as long as it just completes its circular motion. So that can be in seconds, it could be in hours. All right, it is a time essentially, but more specifically, it is the time it takes to complete just one. Now, how are period and frequency related? They're the inverses of one another. So if you, let's say, have a frequency of 2 hertz, that's saying like you doing 2 laps around per second. So if you do 2 laps around per second, how long would it take you to do one? It'd be half, right? Think about it. If you are able to do 2 laps around a little tiny track in 1 second, you have a frequency of 2. The period would be 0.5. It'd be 1/2. They're inverse of one another. So if I know what F is, and I'm looking for T, if I cover up T equals 1 divided by F. So as long as you have one of these, you can solve for the other. Angular speed, we don't really need to go into. That kind of is dealing with the radius of the object, the angle that it's going to want to be moving. We're going to pretty much stick to tangential or linear velocity, sometimes used interchangeably depending upon the source that you're looking at. And this is basically what we were dealing with last week on the interactive, where we had to figure out like what the equation was for centripetal acceleration, which wound up being v squared over r. This basically be like the object's straight line speed at any single point, where if we were to like chop off the force, holding it in place, it would fly off in a path completely tangent in a straight line at a constant velocity. Now, the 2 ways you can kind of solve for that. If you know the radius and either the period or frequency, you can use one of these two. You can use one of those two. So 2 pi times r divided by the period, or 2 pi r times the frequency, and we are going to use that in meters per second. So that is also meaning that you need to make sure period is in seconds, frequency is in hertz, and that radius is in meters for all of that to work. Now for this, So when we were talking about uniform circular motion, if we can like take the overhead view of, let's say, a merry-go-round or a carousel, where you got like the 4 horses on the track. Inside horse, middle inside, middle out, outside. All of these guys are pretty much stuck here on this same spoke of this wheel. All right. Now, this thing is a straight line. It's not going to start curving at all as it's spinning. It's going to maintain a straight line. So if that's the case, right, if this bold black line was the starting line, what is this, pen? If this bold black line here is the starting line, as this thing goes around, and it goes from there to about here, the inside horse will still be here, middle inside, middle out, outside. They'll all wind up keeping their same positioning. But who has to cover the most ground in order to stay in that line? The outside. He has to go all of this distance in comparison, let's just say, to the inside guy. So the farther you are from the center of the circle, the farther you are from the center, you are going to have a greater linear or tangential speed. Now, that is saying it's constant at every point that has the same radius. So basically, like, I don't know how to undo all that. Oh, there it is. Erase. Any point along this radius, right? Obviously, because the horse can't change its radius here. It's going to have the same linear speed or tangential speed. It's going to be the same. And now the rotational speed is the same everywhere. Why? Because they're going to make the same amount of rotations. So the horses that are on this rail are all going to go around the same amount of times. So they will have the same amount of rotations, therefore the same amount of rotational speed. But who has to cover the most distance? The far outside guy. He has to cover the most distance, and hopefully you guys can visually see that. He has to cover they have to cover the greatest distance, so therefore they're going to have the greater tangential or linear speed. So let's say you become parents, hopefully not in the near future, but like in time, and you have your kid with you or your niece or nephew, whatever. If they like to go faster and you take them on the carousel, you're going to want to put them on the outside rail. Why? Because they're going to make the same amount of rotations as the other 3 horses that are on the rail, but they're going to cover the most distance, so they'll have a greater linear speed. So they'll feel like, oh, I'm going faster. And if they don't like to go that fast, but they still want to go on the ride, then you want to put them more towards the inside. Okay. All right. Bam. Okay. Good. No. There you go. All right. So next, problem 1. A biker, he travels or she travels once around a circular track that has a radius of 20 meters in 3 seconds. So calculate the period, frequency, tangential. So by reading this problem, since they go around the track once and it took them 3 seconds, that is their period. Period is 3. To find frequency, it's the inverse. So I know what t is. So if I do 1 over t, I can get the frequency. So 1 over 3 is 0.3 repeating, hertz. And then velocity, 2 pi r over t, or 2 pi r times f. So if I did 2 times pi times r of 20, and then divide by 3, I'm going to get an answer here of 41.9 meters per second. Record player, those things are pretty much becoming extinct. But kind of the same thing. If you put like a sticker here and a sticker here, the guy on the outside is going to move around at a much faster pace. It's going to look like he's moving a lot faster, even though they're going to make the same amount of rotations. So you have a coin that would sit 0.10 meters from the center of a record player, spinning at 45 RPMs. What is the frequency in hertz? So how many per second? Well, if it's 45 per minute per second, we got to divide by 60. So 45 divided by 60 is 75%, or 0.75 hertz. The period would be the inverse of that, 1 over f, which is going to come out to be this 1.33 repeating. And then linear speed is 2 pi r over t, or 2 pi r times f. Either way, you're going to get an answer here of 0.47 meters per second. This was from like an older thing. So we're just going to run through this. Prefix giga means 1 billion. The frequency, if it's 40 seconds, the period would be 1 over 40, which comes out to be 0.025 seconds. If the period is this, what is the frequency? It's the inverse again. If something is running at 2.5 gigahertz, what is the period of the clock? Convert gigahertz into hertz. So you would multiply that by 1 billion and then do 1 over that to get your period. How does the linear velocity or tangential velocity vary with the radius? The farther you go from the center, the greater your linear speed or tangential speed. All right. So think back to that merry-go-round or carousel thing. How does the frequency change? How does the frequency vary? It doesn't. Your rotational speed is going to be the same. You're going to make the same amount of laps around. So it doesn't matter how far you go. Now that's for uniform circular motion. That is assuming that everything on that circular path rotates at the same speed, like it would on a merry-go-round or a record player. All right, so this is something that we did last week. We drew this in one of our assignments. We had to draw in the velocity. This thing is telling us that it's moving counterclockwise, not regularly clockwise. Centripetal acceleration, always pointing towards the center. The word centripetal means center seeking, always points towards the center. We don't really need to go into this. Okay, these are good practice problems. So this thing is moving clockwise. You guys know what clockwise is? That means it starts at like 12 and it goes around like that. So they want to know which vector represents the direction of velocity when the object is located at point B. Velocity is tangent. So if this thing is moving around clockwise, what letter is the correct way that the vector should be pointing? Up? Well, it's going clockwise. So if this was like 12 o'clock and like 6 o'clock, it's going the correct way, like that time should move around the clock. So we're looking at for velocity. Velocity is always trying to be like straight line tangent. So we're looking at D. It should go, that's an awful ass arrow, but it's the best I can do with this thing. It would be going straight down. All right. Next one, number 6. What direction would the acceleration be if it's located at point C? What letter do you think? Mm-hmm. Oh, yes. Give it a shot. No? Well, all right, so the only thing I'm going to say is this. Hold on. Centripetal acceleration, right? What does the word centripetal mean? Now look at this diagram. What direction is the acceleration vector pointing? Towards the center.
Oh, I thought it was a trick question.
No, not trick questions. So then what letter would if what letter here, what vector would show at point C the correct thing? Good. B, because if it was at C going in that direction, it would be pointing towards the center. Next one. 7. What direction would the velocity vector be at point C? It's going around clockwise.
A.
A is right. All right. Essentially, these are what they should wind up looking like. These are your velocity vectors. Now, just imagine they're straight lines because I couldn't quite make them. But those would be your velocity vectors. So, yes, A for that dude. And acceleration at point A would be what? Which one? At point A? Acceleration. Well, I'm sorry, what letter? I couldn't really hear.
D.
Yeah, okay. Just wanted to make sure. All right, because at any single point, the acceleration is pointing inward towards the center. Ba-bam. Bless you. These were just some brief example problemos with centripetal acceleration. So basically taking this equation and using the differences here, like deriving this to solve for either velocity or radius or centripetal acceleration. And the things are here. This is how you go about and doing it. All right, we're not going to spend too much time here going over it. You guys can practice that on the own time. We went through and discussed this. Okay, so in this example, this thing is moving counterclockwise. Guy is holding onto a string, rotating a ball overhead. The force is directed inward via the tension of the string. If that string were to snap, the ball would fly off in a straight line tangent to its path. So an overhead view, centripetal force and acceleration are both doing what? Being pointing towards the center. The velocity is still tangent. Now, if r gets bigger, what do you think would happen to the centripetal force? So basically, right, let's say right off the rip, our radius was 5 meters. If we kept the mass and the velocity the same, but now we increase the length of the string to like 100 meters, do you think the centripetal force would increase or decrease? If you divide by a bigger number on bottom, what should happen to your overall answer? It should get smaller. Good. Okay, well, what would happen then if the radius gets smaller than the original? It's going to increase because you're dividing by a smaller number, so now it's going to give us a larger answer. Well, what if we're trying to spin a heavier object? We don't change the speed or the radius. Do you think it's going to require more force? Yeah. So if the mass increases, the force is going to increase. Those two are directly proportional. And then the velocity, all right, this was something we did pretty much it was on Friday. We went through like that whole simulation thing together. The velocity squared. So if I want to double my velocity because it's squared, I'm going to wind up needing 4 times the force. All right, and that's kind of what is going on in here. In this one, they wanted to show this thing is moving clockwise. So since this is moving clockwise, again, it's doing one of those. Oh God, that's an awful arrow. Shut up. So clockwise will be going, yeah, from 12 to 3 to 6. All right, so which vector below shows the force vector when it's located at point A? The word centripetal means what? Center seeking. So if we're at point A, what direction should the force be going? D, good. Blah, 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 what is Force vector at C. What should C be? Good. What is the direction of the velocity vector at point B? That the middle is acceleration and force. Velocity is tangent. So since it's going around clockwise, it's going to be like one of those, right? These are basically going to be your velocity vectors. It's going to be trying to move in a straight line. Now, if it was counterclockwise, it would be straight up. This guy would be to the left, and this guy would be downward at this angle. Oh yeah, crushing it. So for this one, velocity at B should be straight down. Velocity at point C should be what? A, good. And then acceleration.
Is that when it goes in the middle? C.
Good. All right. Excellent, excellent, excellent. This is excellent practice here. Yeah. Centripetal force for an object in circular motion is 10 newtons. What if the mass doubled? What would the force be?
Or the force double?
Yeah. Yeah, it would double, so it would be 20. And so there's like an equation thing that I used to show you can use if you'd like. So I call it using like the ones equation, where I make everything a one. Now, if it works for you guys, bet. If it doesn't, don't do it. Come on. So this is the force, F sub C, centripetal force. This is mass, velocity squared, and radius. So whenever they're saying something happens here, you can change that value. All right, you can change it from being a one to whatever that thing is. If it's triple, you would make that one a 3. If it was doubled, you make it a 2. If it's halved, you can make it a 0.5, and then just kind of plug it out through there. So like the first one, if they said, okay, if the mass was doubled, this is mass, so I would make this a 2. And then leave everybody the same and figure it out. So 2 times 1 squared is 2, because 1 squared is 1, so 2 times 1 is 1. Divided by 1 is, the answer is 2. So it'd be 2 times the original force. You can use that if you'd like. Okay, well, what if the radius is doubled? Since it's on bottom, I would make that a 2, right? 1 squared is 1 times 1 is 1, so it's 1/2. So what is 1/2 of 10? You're not wrong. Centripetal force. Okay, what if the linear speed or tangential speed is doubled? So mass doesn't change, so it's a 1. If we're doubling the velocity, it becomes a 2, but you still have to square it. So what's 2 squared? 4. Nothing. They didn't tell us anything about the radius, so it stays a 1. So 1 times 4 is 4 over 1 is still 4. So it'd be 4 times the force, and 4 times of 10. 4 times 10 would be. So what if the centripetal force is 10 and the mass is cut in half? Since it's on top, whatever happens to the mass is going to happen to the force. They're directly proportional. So you can know that, or you can change this to 1/2. So 1/2 times 1 is still 1/2. Divided by 1 is still 1/2. So what is 1/2 of 10? Okay, what if the radius is cut in half? since it's on bottom, essentially it's going to be what happens to it. It's going to be the opposite. So if it was doubled, then the force would be cut in half. If the radius is cut in half, it's going to be harder to maintain it, right? If it's at a tighter, like a shorter velocity, it's going to be more force required to maintain the speed at which you were originally at. So what would happen if the radius gets cut in half? Well, if you wanted to do the ones equation, you make this on bottom, and then you can type it into a calculator. 1 divided by 1/2 is 2. You're going to wind up doubling it. So double of 10 is, you're not wrong. All right. So you will have something like this on your homework assignment.
My brain hurts.
I feel like that happens a lot too. Next.
It only happens when I pay attention.
Very funny.
What?
Shh,
I am paying attention.
So this was like another do now that they were required to figure out. Tangential speed. This is your equation, or you can do 2 pi r times f. Now, I would prefer this equation because of what is given to me in the problem. They tell me that there are 3 horses on a rail for a merry-go-round, and they all complete 1 revolution. All right, 1 complete spin or whatever in 9 seconds. Since that is the total time it takes to make 1, that is period. That is capital T. So basically, you're literally just doing 2 pi times r divided by 9 for each one of these. That's all you would have needed to do.
Okay. Yep.
No, that's fine. Yes.
No,
So and what you would see is what you should wind up seeing as you do this, that
2 pi times like 3.5 divided by 1.
Yeah. Right. So I'm just gonna throw it into the calculator real quick. So 2 pi times 3.5 divided by 9. So it's like 2.44. The next one going to be by times 2 pi 7 divided by 9, 4.88. And then 2 pi times 12 divided by 9, 8.37. So you should see that as you are getting farther away, you have to basically move at a faster speed in order to stay on that, keep up and stay on that path. Like if I were to look at what the hell is it? This thing, the overhead. So the guy on the outside needs to move at a faster speed in order to stay in line with the other horses. So you have a radius here. You spin 3 times in 1 minute. So that is in RPMs. Divide that out by 60 to get your period. 2 pi times r divided by the period will give you the velocity. You have mass. So mv squared divided by r to give you your answer here. We're not going to go into other pieces of that. So centripetal force equation, mv squared over r, or ma sub c. You can rearrange it to find these guys. And what force plays the role of centripetal force when a car rounds a curve? Well, you have the weight of it going down, you have the normal force going up, velocity is tangent, you have the friction force inward, therefore it's going to be the direction of our acceleration. All right. All right, so now I posted, guys, the homework for you guys. So with this, all right, via the notes that we just kind of went through and the couple days last week that we spent on this, You guys should go through and you're going to answer a couple of these multiple choice questions. You will double click on this, John, to edit and draw in what they want, the acceleration and velocity vector for this thing. All right, at the dot here. Double click on it to edit. Go up top here. You have your arrow. You can move it around to however you need. Bip, bop, bop, boop. Save and close when finished. This, you may not actually need all of these here, but these are just things to know. Period is capital T. Time it takes to make one cycle. Period is measured in seconds. Frequency is measured in hertz. Radius needs to be in meters. Centripetal force, newtons. Centripetal acceleration, meters per second squared. Velocity, speed, tangential velocity, tangential speed. V is in meters per second. Frequency, F is the number of cycles per second. And a couple other extra equations here. Now, I believe for most of these calculations, you guys are going to be using basically like this. Oh shit, what? Whoa, buddy. Whoa, buddy. Hold the phone, Cotton. There should be an M right here. That should be mv squared over r. Well, I mean, you have the equation there. You have centripetal force here if you needed that. Excuse me? Okay. We're not allowed to erase here. Sick, dude. All right. It's good. I'm happy about that. All right. Anyway, they want centripetal force here. You are given a mass. They tell you what the radius is. It's already in meters, and you have a tangential velocity. So you're using mv squared over r. Answer in newtons. Okay, up there, they're gonna follow. They're gonna come down with us. Cool. Velocity. So if you're looking for the velocity, you're going to be using this piece here. I would like to circle it again, but now I'm just going to have a bunch of dots on my screen, which is sick. Don't want that. So velocity, you're going to take the centripetal force given multiplied by the radius divided by the mass and then square root it. These ones here, if the centripetal force is 8 newtons, what would it be if the mass doubled? We just did problems like that in the notes. And then this little last piece here, basically is like horses on a rail. Inside, middle out, out. Rotational speed. They should all make the same amount of rotations around, so they would have the same rotational speed. But as far as tangential speed, who needs to cover the greatest distance in order to keep up with everyone? And then you rank them. And then there are some matching guys here. All right, so that, guys, is what your assignment is going to be. Start working on it now. And if you have questions, you can ask.